Hello, everyone. So far in the course, we talked mostly about differentiation. So differentiation dealt with finding derivatives, which represented the rate of change or the slope of a tangent line. But this is only one of the two halves of calculus. So the other half of calculus deals with integration, which is another process that looks at finding areas and volumes and accumulation and so on. And these two halves are connected by something called the fundamental theorem of calculus. So to understand the fundamental theorem of calculus and to actually use it, we're going to need to understand something called derivatives, which we're going to talk about now. And luckily, antiderivatives are an easy, just an easy consequence of understanding derivatives. Basically, an antiderivative just means look for a function whose derivative is the thing I started with. So it's basically the opposite of taking, or the reverse of taking derivatives. So let's look at this. So here is pretty much what we just said. So capital F is an antiderivative of little f if the derivative of capital F is equal to little f. So it looks kind of confusing, but all it means is if I start with little f and I want to find an antiderivative, then that means I have to look for some other function whose derivative is little f. So finding an antiderivative of something, it just means look for a function whose derivative is the thing I'm starting with. So rather than taking a derivative, we're looking for something whose derivative is the thing we're starting with. So for instance, an antiderivative of cosine x is sine x. So we're looking to undo differentiation or look for something whose derivative is cosine x. Okay, that would be sine x because the derivative of sine x is cosine x. Okay. However, so is sine x plus c for any constant c. So if we differentiate sine x plus 1 or sine x plus 10 or sine x plus c for any constant c, we're going to get cosine x plus 0. So we're going to get back exactly cosine x. Okay, so antiderivatives are not unique, unlike derivatives, but they are unique up to adding a constant. So actually, any antiderivative of cosine x would always look like sine x plus c. Okay, so here is that what we just said, basically, but phrased. So if we know one antiderivative of a function, then we can get them all just by adding on constants. So they're all of the form, the same form, capital F plus C, where C is an arbitrary constant. And this is called the general antiderivative. General because it represents all of them, I guess. So for instance, the general antiderivative of secant x times tangent x, that means we have to look for a function whose derivative is secant x times tangent x. Well, we know from our rules on derivatives that the derivative of secant x is exactly secant x times tangent x. So if the derivative of secant is the thing we started with, that means secant is an antiderivative. But we're asked to find the general antiderivative, so we have to add on this arbitrary constant c. So the general antiderivative is secant x plus c. Okay, and similarly with 1 over x, we want to look for a function whose derivative is 1 over x. Well, if x was positive, then we could take just ln x. But if we don't know that x is positive in general, ln x only makes sense for x bigger than 0. So in general, we're going to want to use ln absolute value x. And we did remark that the derivative of ln absolute value x is 1 over x. So this is good, but then we want the most general antiderivative, so we have to add on this arbitrary constant c. So the general antiderivative will be ln absolute value x plus c. Okay, so moving on. So we're going to get a lot of rules for antiderivatives just by reversing rules that we already have for derivatives. So how about if we have a function, say, which is a sum of some simpler functions, and we want to find an antiderivative? Well, basically, if it's a sum or a constant multiple, we should just find the antiderivatives of the pieces and add them together. So here, for instance, suppose we have two functions, little f and little g, and we know two antiderivatives, capital F and capital G. How do we find the antiderivative, say, of constant times f? Okay, it would just be a constant times the antiderivative. And how do we find the antiderivative of little f plus little g? It would just be the sum of the antiderivatives. So what we are saying here is that if we have like a sum or a constant multiple of something, we want to take the antiderivative, we just do the antiderivative of each piece separately. Okay, so here we're not doing products or quotients or compositions or anything complicated like that. We're just doing sums and constant multiples. In that case, we can just take the antiderivative of each piece. Okay, and since antiderivatives are basically reversing derivatives, all the derivative rules we use can be used to give rules for antiderivatives. So here are some of the main ones that are going to be useful for us. For instance, the antiderivative of x to the n, where n is not minus 1, is x to the n plus 1 divided by n plus 1. Why? Because if we differentiate x to the n plus 1 over n plus 1, and we use the power rule for differentiation, we're going to get n plus 1 times x to the n over n plus 1. The n plus 1s are going to cancel. We get back exactly x to the n. Okay, so the derivative of anything on the right is going to be the function on the left. So the antiderivative of the function on the left is going to be the function on the right. Okay, so 1 over x we already talked about. E to the x is straightforward. B to the x, normally if we differentiate b to the x, we get b to the x ln b, which means we multiply by ln b. If we're doing the antiderivative, that means we have to divide by ln b instead. Okay, derivative of sine is cosine, so the antiderivative of cosine is sine. Similarly with the rest of the trig functions here. Derivative of inverse sine is 1 over the square root of 1 minus x squared, so the antiderivative of 1 over the square root of 1 minus x squared is inverse sine. And similarly with the 1 over 1 plus x squared and tangent inverse. So we get all these rules just by reversing rules we already know for derivatives. It's not like you suddenly have lots more rules to remember. You can just kind of store them next to the rules for derivatives that you already remember for the ordinary derivatives. Okay, and here, of course, I didn't write plus c in every case, but if you want the most general antiderivative, you have to write plus c. So if you're ever asked to state or to find the general antiderivative, make sure you do add the plus c in. So, and there are many ways that they could ask these types of questions. For instance, here, let's try to find all functions g that have this as derivative. Okay, what does that mean? We're looking for a function that has this as derivative. We're looking for the antiderivative. So we're trying to find the antiderivative of this. So that just means we have to take the antiderivative of each piece and the sum, and then add together the antiderivatives. So if we want the antiderivative of 4 to the x, we use the rule for b to the x with b equal 4. We're going to get 4 to the x over ln 4. If we want to find the antiderivative of x cubed, we use the rule for x to the n, where n is 3. We get x to the 4 over 4. 5 over x, we use the rule for antiderivative of 1 over x is ln absolute value x. We get 5 ln absolute value x. And we want the most general antiderivative, so we have to add on that plus c. So here is the general antiderivative. And sometimes we might be given more information. So suppose we were told the value of g of 1 or g of 2 or something like that. Then we could use that to set up an equation. And instead of having that arbitrary constant c, we could use extra information to solve for a particular value of c. So this is called the particular antiderivative. So if we find our general antiderivative and then we have some extra information that actually helps us find a fixed particular value of c, say c equals 1 or c equals 5 or whatever, then that's called the specific antiderivative or the particular antiderivative. So here's an example where we can do that. So let's try to find f if f prime of x has this formula, and additionally we know that f of minus 1 equals 2. Okay. In this case, the general antiderivative, we just take the antiderivatives of each piece. We get x to the 5 minus x cubed plus 4x plus c. And then we have this extra knowledge that f of minus 1 equals 2. So we can use this to set up an equation. So if we plug f of minus 1 into our equation f of x, it involves c. So if we plug in x equals minus 1 here, we're going to get minus 1 plus 1 minus 4 plus c. So this is f of minus 1, where we used our equation involving c. And then we know that's supposed to be equal to 2. So we can use this to set up an equation. We can solve for c. The minus 1 and plus 1s cancel. We move the minus 4 over. We get c equals 6. Okay, so now we can repeat the antiderivative, but now we know that c equals 6. This gives us the particular antiderivative. It's just the general antiderivative with a specified value of c. So here c equals 6. So this is the particular antiderivative. Okay, lastly, one application of antiderivatives is, we said that the derivative of displacement is velocity, the derivative of velocity is acceleration. So now we can undo that. So if the derivative of velocity is acceleration, then the antiderivative of acceleration is velocity. And similarly with velocity and displacement, the antiderivative of velocity will be displacement. So for instance, here is an example where we use that. So let's say a particle moves in a straight line with acceleration a of t equals 6t plus 4. And we're told the initial velocity is minus 6 centimeters per second. The initial displacement is 9 centimeters. We want to find the position function s of t. So this is a question really about antiderivatives. So we know a formula for the acceleration. First step, we find a formula for the velocity by finding the antiderivative. So the antiderivative of acceleration is velocity. So this gives us the velocity is the antiderivative of 6t plus 4. So we do the antiderivative of 6t. Antiderivative of t being t squared over 2. We get 6 times t squared over 2. We get 3t squared. Then we have to do the antiderivative of 4, which is 4t. And then we have to add on a constant. And you could use c here, but there is going to be another constant in a second. So I decided to write c1 just to distinguish it from the other constant. So this is our general antiderivative of the acceleration. So now we have this extra piece of information that v of 0 is minus 6. So if we use that, we set up an equation. If we sub in t equals 0 here, we are going to get just c1, and that's supposed to be equal to minus 6. Okay, so here c1 should be, sorry, this should be minus 6, not plus 6. Okay, so v of t is going to be 3t squared plus 4t minus 6. Okay, now we do the same thing again. We find the antiderivative. So the antiderivative of velocity is displacement. So we first find the most general antiderivative. Our displacement is t cubed plus 2t squared minus 6t plus c2. So with a different constant. Each time we do the antiderivative, we might get a different constant. There's not necessarily any connection between C1 and C2. So now we want to use the information that S of 0 equals 9 in order to solve for the constant C2. So if we plug in t equals 0, we are going to get C2, and that should be equal to 9. So we know that C2 is equal to 9. Okay, so now we can write out our position function. S of t is t cubed plus 2t squared minus 6t, and then we said our constant is plus 9. Okay, so that's about it for this video. So what did we say? We said, okay, if we want to find an antiderivative of something, that means we have to search for some other function whose derivative is the thing we started with. So it's basically the opposite process to differentiation. We can use a lot of rules we have for derivatives. We turn them around, we get rules for antiderivatives. There was something called the general antiderivative, which is one antiderivative, and then we have this arbitrary constant c, so that it actually represents all the derivatives. All the antiderivatives. And then if we have extra knowledge, we can use that extra knowledge to plug in and find the constant c. And if we manage to find a specific value of c, then that's called the specific or the particular antiderivative. Okay, that's it for today. Thanks everyone. See you next time.